Can you hear me now?
You're not on yet.
Okay, let's see.
Maybe it's not the same URL. Oh, there.
Yeah, it is. Hello, hello. Can you hear me? Yeah, you can hear me now?
Yeah, it's kind of blurry though.
The sound or what?
The video is blurry.
Are you
there it's focusing a little bit.
Yeah?
Don't worry about that.
Well, maybe I just gotta put it back a little bit. I don't know.
I think we can start.
Yeah. Oh, let me move aside. Can everybody hear me? Little glitch there. I have all these technical glitches, technological glitches. Sometimes they come out of nowhere. You have no idea how you get into that trouble, that kind of trouble. Anyways, today I was saying, before I was shut off by the mic, I'm going to be doing a little brief history of not of time, but of motion. What is motion? And when you look at it from a historical point of view, you find out that very few people dealt with the subject, and whenever they did so in a religious context. They wanted to know if the soul moved, or if the soul was the prime mover. And obviously they discussed the issue of whether there was a first mover, an unmoved mover. But I'm getting ahead of myself. Let me just start here at the beginning. And I'm going to start with the Greeks. They're the ones who left written word in general about the first notions of physics, geometry, etc. And they did so in a somewhat organized fashion, in the sense that they debated these things among themselves, and then they published, they wrote something. And what I'm going to start with is with Plato. And you have to recall that Plato invokes other people who do the talking for him in all his dialogues. And of course, one of those is Socrates, and I'm sure that some of these ideas were already kicked around with Socrates and his students before Plato wrote them, a few years later, after Mr. Socrates had the good fortune of drinking some hemlock. And so, let's start with Plato here, and I got a statement from him, and this comes out of the Timaeus. And he says, let me move aside here a little bit and see if I can make this a little bigger. Motion never exists in what is uniform. For to conceive that anything can be moved without a mover is hard, or indeed impossible. And equally impossible to conceive that there can be a mover unless there be something which can be moved. In other words, we can't have a mover without something to move, and we can't have something to move without a mover. Okay, that was the original thought. That was the original train of thought, the philosophy. Motion cannot exist where either of these are wanting, and for these to be uniform is impossible. Wherefore, we must assign rest to uniformity, and motion to the want of uniformity. Okay?
What does that mean?
Yeah, well, you gotta drink a lot of tea to understand that one. Essentially. But what I'm looking at here, this is one of the first statements he makes. What I'd like to focus on today is really definition of the word motion, and also how it relates to physics. Because like I just said a minute ago, the word motion has been investigated, but mainly for people who were talking about the motion of the soul, the movement of the soul, and also if there was a first mover, or how did things start getting in motion to begin with. And if you think of gods and things of that nature, then you have to try to justify them on the basis that that guy is the first mover. And that's what you're going to see in the first few people who deal with this subject. Okay, so the next one, he tries to give a definition here. Mainly, he says that there are 6 directions of motion. There's wandering backwards and forwards. There's right and left, and up and down. Those are the 6 motions that he defines, or describes at least, in Timaeus. And
this is Plato?
Yeah, but then he adds another motion, because he's got to justify the motion of the celestial spheres, in which he says are spheres. Okay, this is interesting because the Greeks already had an idea that the world was round and not flat. Some people still today try to make you, believe in. He says the movement suited to this spherical form, he's talking about the earth here, was assigned to him. Being of all the seven, he's talking about the seven motions here, that which is most appropriate to mind and intelligence. And he was made to move in the same, he's talking about a God here in a sense, and he was made to move in the same manner and on the same spot, within his own limits, revolving in a circle. All the other six motions were taken away from him. In other words, the earth here is not going to be able to move back and forth, up and down, or sideways. The earth can only move in circles, and he says that the earth is spherical. And he was made not to partake in their deviations. Okay, so apparently the Greeks already had a notion that the earth was round, spherical, and then they tried to explain the motion, the circular motion. They realized that it was moving some kind of circles. There was constant repetition in the sky. Not only the sun and the moon, but the constellation. They probably noticed that as well. And so they're trying to justify this. And how do they justify it on the basis of circular motion? It's not going to be until Kepler who comes up with the ellipses. Okay. And so what's the origin of motion? Well, here Plato tells us. He says, and here, let me make that a little bigger. Then we must say that self-motion, being the origin of all motions, and the first which arises among things at rest, as well as among things in motion, is the oldest or eldest and mightiest principle of change. And that which is changed by another and yet moves another is second. In other words, he's saying that the guy, if you see something in motion, that's secondary. That means that guy was already moved. But the first mover, the first thing that ever moved, has to have self-motion. This is his argument, okay? It's going to be challenged by Mr. Aristotle. And he says, and here I want you to focus on the definition also of motion, because Aristotle gives us one. But he disagrees with Plato, and I'm going to show that later on when I get into St. Thomas Aquinas, who essentially summarizes both of them. But he says, Aristotle says, does it follow that being, if one, is motionless? We're talking about God here, right? The original source of motion. Why should it not move? The whole of it within itself, as parts of it do, which are unities. Which are unities. This water, that's an example, right? Again, why is qualitative change impossible? And that's where I want you to focus, on the fact that Aristotle defines motion as change. Okay? He's giving a synonym, essentially. He says, again, why is qualitative change impossible? So that's how he defines motion. He also has another synonym, Aristotle, and he brings that up in his third book of physics. Okay, and he says the fulfillment of what exists potentially is so far as it exists potentially. He says motion is potential made actuality. Okay, so what was potential, the possibility of movement, is made actuality, and that's essentially what motion is. But he says of what is alterable, qua alterable, alteration. Okay, so Aristotle is essentially defining motion as alteration and also as change, as you saw in his previous note. So he's using synonyms. He's not really telling us what he means by motion. He's just using these synonyms. He's saying, in this case it's change, and the other one he uses the word alteration. Okay, and nothing much happened for hundreds of years until we get Mr. Thomas Aquinas in 13th century. And he essentially uses Plato's and Aristotle's definition, which shows again that nothing much happened throughout those years as far as discovering or defining the word, what motion is, or defining what the word motion means. And Aquinas says everything that is moved by another. Now, he gets this from Aristotle, okay? He essentially is an Aristotelian as far as motion. He's going to use this argument to prove the existence of God. What is he after? He's after Aristotle's unmoved mover, the first source of motion, okay? That's what he has in mind. And so he takes Aristotle. He's going to do a little bit of Plato in a second here also. But he says everything that is moved by another. This mover is itself either moved or not moved. Okay? If it is not, we have reached our conclusion, namely that we must posit some unmoved mover. This we call God. Okay, that's the unmoved mover, the man upstairs. If it is moved by another mover. We must consequently either proceed to infinity or we must arrive at the same unmoved mover. Okay? Now, it is not possible to proceed to infinity, hence, we must posit some prime unmoved mover.
He just threw away the infinity part. He didn't like the infinity.
He didn't like it. He wasn't a mathematician. He wanted to. But again, all this is related to the soul and God and the Bible and Christianity. Okay. So Aquinas is again, and Plato did the same thing, by the way. Plato used this notion of the self-motion, and he ascribed that to the soul. Okay? He says it's the soul. He says a body, you have a body and you have a soul. The soul enters the body, right? And that's the ether I talked about the other day, where the ether comes from the stars, and he penetrates your body, and the soul is what you are really, that spirit that you have inside you, okay? And he says that's the guy that's going to do the moving. The soul is the origin of motion. Okay, the body is just a statue until the soul penetrates it. That was Plato's idea, and Aristotle disagreed with that, saying, well, he was a little more materialistic, and he said, well, it's not really the soul; it's that there was a first mover, the unmoved mover. So now we have two concepts here: the soul from outer space, or from the ether, or from whatever that comes into the body and gets it moving, and that's kind of like a concept, but again, you have to remember Plato assigned a form to the soul. Okay? And then you have Aristotle, who says, look, there's an unmoved mover. He's the guy who set the dominoes in motion. Okay? That's the difference.
Isn't this self-moving soul kind of how you define life, that which moves by itself? What is itself kind of thing? They're trying to give it this, the soul is the itself part.
In a way, that's an interesting comparison, because a rock moves, but a rock requires a mover. Like both Aristotle and Plato agree with me there. It requires a mover, but the living cell, it doesn't require a mover. It starts moving by itself, and now that's scary, because we say, hold it, what is a cell? Well, a cell is a bunch of atoms, a bunch of molecules, it's just strands.
It's small rocks moving on themselves.
Kind of like that. We have all these rocks, we'll call them atoms, and they're lifeless, but when they get together and have a party, it's kind of like they imbue life into this thing we call cell, which is the unit of life. And suddenly the cell begins to move, and that is quite scary, if you're, I don't know, I guess if you're God or you're an intelligence out there in the universe, and you see that all these rocks are just performing regular motions, spinning around each other and spinning on their axis and all that stuff, and everything's fine because everything is predictable. And suddenly you come across unpredictable motion, which is a cell that moves in the opposite direction. And you say, oh, what is that? What happened there? That must be scary, even for God, But anyways, this is what St. Thomas says, okay? And that we have to have an unmoved mover, and he gets that from Aristotle. But he takes care in giving credit also to Mr. Plato. He doesn't get rid of Plato completely. In fact, he's trying to blend Plato with Aristotle. He's saying they're talking about the same thing from two different angles. That's essentially what these two guys are doing. And he says the following about it. He says, and this again is in the 13th century, and I'll have to split it in two here. It is to be noted, however, that Plato, who held that every mover is moved, in Phaedrus, right, understood the name motion, or the term motion, I guess that's what he meant, in a wider sense than did Aristotle. For Aristotle understood motion strictly, according as it is the act of what exists in potency. In other words, Aristotle said that it's potency made actuality. Okay, that's what motion is. Whatever those two words meant for him. But whatever was potential now is made actuality, and that's called motion. And so it exists in potency inasmuch as it is such. So, understood, motion belongs only to divisible bodies, as it is proved in the Physics, number 6, chapter 4. According to Plato, however, that which moves itself is not a body, even though he talked about the form, okay? He's talking about the soul here. Plato understood by motion any given operation, so that to understand and to judge are a kind of motion. Aristotle likewise touches upon this manner of speaking in the Anima, book 3, chapter 7. Plato accordingly said that the first mover moves himself. Okay? What my son just said, the cell kind of moves by itself. It moves himself because he knows himself and wills or loves himself. So the reason the original mover of himself moved was because he loves himself. That goes for all you egotistic people out there, okay? So if you love yourself, you're in motion. In a way, this is not opposed to the reasons of Aristotle. Look at this. He's saying that even though they come from different angles, they're not disagreeing really on the primary mover, which he's going to end up with God, right? There is no difference between reaching a first being that moves himself, as understood by Plato, and reaching a first being that is absolutely unmoved, as understood by Aristotle. So we have a being that is unmoved, that's God, and a being that can move himself, and that's also God. And so they're just talking about two different aspects or properties of God. The ability to stand still, completely still with respect to everything else that exists, which is nothing at that point. So God can stay absolutely still, not move a single part of his body. And at the same time, God has that ability, that magical ability to start motion within himself, as either within himself or as a complete entity. And that entity is now going to set the dominoes in motion. He can move anything else that he wants. Okay, so those are the notions. But remember, all this is related really more, except for Aristotle. I'll give him a little credit because he's trying to explain a little bit about physics, even though he mentions the gods a lot. But Plato and everyone all the way to Aquinas, they dealt with this issue only on the basis of what the soul is and who the first prime mover is, which is God. So it was all related to religion, not really to physics. It's not like they went to a lab and they said, well, what is motion? How do we explain it? No, they were trying to justify the Bible. And they said, well, what is motion? Or how do we justify the existence of God? And one of the 5 arguments that St. Thomas has is that he's the unmoved mover. That was his argument. And he essentially takes Aristotle and develops him in about 35 arguments.
Well, this prime mover thing is something that even physicists hit upon with the Big Bang, where it's like everything's in motion. Well, if we track back where everything came from, what is the prime mover? Instead of God, they put this explosion.
Well, what I'm
trying to say is everyone has this feeling that the universe is this billiard table where all the billiard balls are moving, but everyone tracks it back to either these things were always in motion or someone hit the first ball with a stick. And everyone kind of throws the first one away because everything always being in motion just sounds ridiculous or something.
Because there's no everything.
Yeah.
But there's another issue there, and remember Stephen Hawking, he in his book, A Brief History of Time, he does go in there and talk about energy splitting from energy, positive from negative. That's how he creates the universe. In other words, there's nothing, but nothing is the blend of positive and negative energy. And where that energy came from is never explained, and it's just given as a hypothesis. You have to grant it. You have to concede it's an assumption. And so there is energy, whatever energy is, because energy is a concept, but it turns out that this concept separates physically, because now we're going to talk about physics, separates physically into positive energy and negative energy, which he names mass, positive energy, mass, negative energy, gravity. Okay, so now we have gravitation and mass. Now we're talking about, at least in the case of mass, people, at least in their minds, they think, well, you're talking about now something, a physical object. You're talking about something existing, right? Mass, a table has mass. A table is a physical object. So when you get into the word mass, it's like suddenly energy morphed into a physical object. And again, since we're talking about motion, the point that I'm trying to make here is that the way Hawking explains it, you have motion of energy, self-motion of energy. Somehow the heavens split apart, and you had positive energy here, negative energy over there. So now you start getting matter from absolutely nothing, which is energy. So if that makes any sense to you, but that's the reasoning. If you have energy, and energy is the blend of gravity and mass, and you can use the euphemisms or metaphors called positive and negative energy. Well, when you split them apart, now you have real things in the universe. So again, something from nothing, okay, in a sense.
So if you split space, you have mass. And it did it all by itself.
In fact,
it's
today,
its own prime mover.
In fact, today we have another angle to that same notion, to that same concept, and that's that in the vacuum, the vacuum, especially in the when they go to the accelerators, they split space. They pull particles out of space, right? And so you can say that when they're in space, they're like in this mass of particles that don't move. You would think, because at least Newton held that space does not move. He figured that one out. But now we're pulling a particle from space, a virtual particle, comes into detection, into visibility, into whatever you want to call it, just somehow gets taken out of that mass of space that's surrounding us. The particle comes in, does its job, because it lasts for a very split second and goes back to where it was. And so there is motion. The particle is moving. I mean, you would have to think that they're talking about some kind of motion. The particle is coming out of the space. That alone is motion. And then he goes back into space. That's motion too. So again, we have all these subtle motions out there that nobody really justifies or explains. Okay.
Hide the text.
I'm gonna try to get. Let's see. Okay, I can.
It's kind of too blurry anyway.
The image is blurry, coming out blurry.
Yeah.
Let me see it. I see. Okay. Well, I don't know why it's blurry. Okay. So what do we have now? Well, we have. Then comes Newton. He comes in the 17th century, and that's 400 years after Aquinas. Okay. And he's the first guy who tackles the word motion again. Well, not true. I mean, we had other people like Descartes and so on. I'm not going to look at all the milestones because there were no milestones. The next milestone is really Newton. And what does Newton say? He says, I do not define, and he says this in his scholium. He writes this in his scholium, which was written in Latin. And that's a scholium to Principia, his main work. Okay. 1689 edition says, I do not define time, space, place, and motion as being well known to all. So since we all know what motion is, why define it? Why take the trouble? We don't have to define it.
Sounds like he cheated.
Yeah, in a way, because, keep in mind that Newton's been credited with the 3 laws of motion. First law, second law, and third law, right? And so they're called laws of motion. And you would think that the guy who invents or discovers the laws of motion he would at least define the word motion, what he's talking about. And here Newton starts, I think it's the third sentence down, says, I do not define motion as being well known to all. So if we know what it is, why should he take the trouble to define it? But he does give a little definition there right after that, like 2 paragraphs or 3 down, and he says, absolute motion is the translation of a body, blah, 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 blah. Okay? So he uses the word translation, again, a synonym, because if you look up the word translation, well, what does it mean? It's motion. I can't imagine translation without motion. And again, whether you use the word change or alteration as Aristotle used, or translation as Newton uses, you still don't know what motion is, because all these people are using synonyms. Okay? And but what I like about Newton, he also defines rest. We have motion, but we also have rest, no motion. Real absolute rest is the continuance of the body in the same part of that immovable space, in which the ship itself, he gave an example of a ship, right? Its cavity and all that it contains is moved. So he's saying the ship is moving, but you're not moving with respect to the ship if you stand in the same place. So what he's essentially putting here, I think, this is the first notion of this, of the frame of reference, which is going to be used later on by Einstein and all these other folks to justify, position. What is your position? Well, what is the frame of reference? So again, Einstein uses this as a relative motion or relative location position, as they call it in math. And I think Newton's the first one to come up with this. He's saying, if you stand on the ship and you hold the same distance from the walls and the ceiling, you always stand still there, even if the ship moves, you don't have any motion with respect to the walls of the ship. And that's what he talked about when he says absolute rest. He's introducing essentially the concept of frame of reference. Okay? And we don't see any, you have Maxwell also. He came up with laws, but he never defined motion as per se. And neither did any of the other folks like in the 19th century. It never happened. But we have Mr. Einstein. He comes in 1905 and he writes an interesting, one of his 4 annus mirabilis papers. And the paper, I'll read, it's called On the Electrodynamics of Moving Bodies. Now, if he's going to talk about moving bodies, you would think that, well, as a minimum, he would define what moving means. What does moving mean? I mean, when you call the movers to move your stuff from your house, we pretty much know what moving means, right? But here we're talking about a scientific paper, right? And this is the only notion that he puts in that entire paper, the closest he gets to a definition or a description of motion. He says, if we wish to describe, right, the motion of a material point, okay, we got a point, but it's material, okay, we give the values of its coordinates as functions of the time. So he's talking about frame of reference again, talking about Cartesian coordinates, and he's talking about time. He introduces time to try to justify motion, okay, or describe or define motion. Now we must bear carefully in mind that a mathematical description of this kind has no physical meaning unless we are quite clear as to what we understand by time. And of course, the entire paper is not about motion. The entire paper is about time. Okay, he wants to show that time is relative.
Is that because he's basing his definition on, you can't define motion until you define time in his eyes, so he goes after that one first?
I'm not sure that's the case. I think that he simply, like Newton says, well, we all know what motion is, so I'm not going to, in a scientific paper, begin by defining motion. So it's like, we all know what motion is, so let's worry about time because we don't know what that is. And what he showed in this paper, which is, I guess, the early special relativistic paper, which did not get developed until 3 years later, 1908, thereabouts. In this paper, he's kind of giving a hint of what he's up to. He's going to show you a relativistic time. He's going to start saying it all depends on the observer. And that's why he introduces the notion of frame of reference, and why he introduces the notion of time to justify motion. So when he talks about, the title is very misleading. He says on the electrodynamics of moving bodies, but he's not going to talk about moving bodies. He's going to talk about time. That's what he's interested in. Okay, so yeah, it's, in a sense, he's using time to define motion, which it should be the other way around, because I'm sure we're going to talk about motion before we introduce an observer. And time you won't get until you get an observer. You need memory to talk about time. You don't need memory to talk about motion. And my definition at the end of the talk will show that, okay? But we get to, in between, there's just a comment I want to make, and that's that Mr. Heisenberg, Werner Heisenberg, in 1927, he comes up with the famous uncertainty principle, or principle of indeterminacy. And that's a funny one, because essentially, and the way I'm going to interpret it, he says that, the more you know about the position of a particle, the less you know about its momentum, and vice versa. The more you know about its momentum, the less you know about its position. And what I'm saying is that what he just said is that when the ball moves, it doesn't stand still, and when it stands still, it doesn't move. No kidding. So talking about motion here, you're talking about, again, another scientific paper. This one garnered Werner his Nobel Prize. And what did he say? He said essentially that, when you know more about, when a ball starts rolling to a point where it stands still, at that point we don't know anything about its motion. And when it starts moving again, we know very little about its position. And again, it's just this idiotic principle that underlies quantum mechanics. But anyways, what do we get to? Today, what do we have? Do we have any good definition that we can use? Well, this is the definition I found at the Wikipedia. And the Wikipedia says, in physics, motion is a change in position. Change in position of an object over time. So they also introduce time. And when you look up the word position, it says a Euclidean vector that represents the position of a point P. So they use the word position to define position in space in relation to an arbitrary reference origin O. Okay, so he's saying that position is a vector. And we don't know what position means because he uses the word position to define position. But the point here is that if you put that word position or that phrase into the first definition, you say motion is a change in position. And what is position? Position is the position of a point. That's what a position is, okay? And they add, motion of a body is observed by attaching a frame of reference to an observer and measuring the change in position, again, change in position of the body relative to that frame, okay? So in other words, this is all mathematical stuff that they want to introduce as science, and they say, look, you want to know what motion is? Well, first we need to get a frame of reference, okay? A Cartesian coordinate system of some kind. And once we get that, we get a position, and then we have a change in position with respect to that coordinate system. That's it. That's the notion or definition or description of the word motion today, officially. And then if you look at it in the Dictionarycom, also has a definition which is pretty much in the same line of reasoning. They say the action or process of moving. Motion is the action or process of moving or of changing place or position. A change is motion. And another definition in that same, from another dictionary within Dictionarycom says the process of continual change in the physical position of an object. So that's it. We have, what is motion? It's change. And if you look up change, it's motion. You can't do change without any kind of motion. So we don't know what the definition is unless we use a synonym. And from Einstein all the way to the Greeks, we had the same problem. No one really defined the word motion. They never knew that in a scientific way, in a way we can use it consistently, in a rational way. And most of that history, if you go through there, is related to God and to the soul. They wanted to show that at all costs that there is a prime mover or unmoved mover. And they also worried about whether the soul moves. And the soul obviously penetrated your body and got you to move. So you didn't move. You were just a little statue that until the soul penetrated your body, you had no motion. And so those are the notions we had throughout history. Now, why am I concerned about this? I'm concerned because, one of the things that you'll note is that this is a very key word in science. You need to know what motion is in science, like you need to know what an object is in science, in physics. You can't do physics without an object, and I'm sure you can't do physics without the word motion. You're going to use the word motion in some way or another. Newton's equation, acceleration. You also have momentum. What are these words? Well, these words represent motion. You have velocity. What is velocity? What is speed? What is the speed of light? You're talking about motion. So you can't do physics without either the word object or the word motion. And neither of these two words have ever been defined. So I'm going to take a crack at it. In fact, I did, and a lot of you already are familiar with it, but I'll put it up here so that we know where we stand on this issue. I do define these words. I think you cannot avoid them. Object, that which has shape. Distance is the separation between objects. Location is the distances from all objects to the target object, to the one in question. And motion, two or more locations of an object. Now we're not using synonyms, because location or object are not synonyms of motion. And we're saying what motion is, what we mean by the word motion. If you have an object and it occupies at least two locations, then you have motion. And what is a location? Well, if you take the set of distances from that object to all the rest in the universe, that's its location with respect to absolute location with respect to the rest of the matter in the universe. And what is distance? It's a separation between objects. What is an object? That which has shape. Period. So we don't get into this fancy stuff of who's the primary mover, or was there an unmoved mover, is the soul an object, no, I don't define motion because we already know what it is, or start giving like Einstein his presentation without defining what motion is when he's talking about the moving bodies. No, here it's straightforward, and these are concise, they're crisp, they're rigorous. And rigorous only because we can use them consistently. That's what I mean by rigorous. And again, motion, two or more locations of an object. Now you can understand what I'm saying. If I show you a film and something is moving in there, for sure, in each frame of the film, I'm going to have a different location for that object. And you can split it up as many times as you want because motion is not discrete in that sense. Motion is only discrete in the sense that it's built up of locations. But locations of an object in the universe is like Plato and Aristotle also thought about them. They said, well, it's continuous. It's like it's not chopped up, and motion is not chopped up. But for the definition, you need to chop it up because it's based on the notion of location. Location is a static concept. Location means that, I'm not going to move anything. I'm just going to define location. That's a set of distances from all objects in the universe. That means at that moment in time, he took a snapshot of the universe. God took his camera, took a picture of the universe, and says, that's the location of this atom in the universe. Okay? Now, if that atom in the next frame is found somewhere else, now we have motion. You need at least two frames of the universal film to conceptualize motion. Is motion discrete? In a sense, yes, and in a sense, no. It's not in the sense that it's built of location, and each location is a discrete entity because it's defined as a static concept. But motion is obviously continuous, which is the wrong word. Again, I use the word incessant. Motion is incessant.
Are you saying two or more locations of an object?
Yeah. And
you're saying location is a distance from all objects to the target?
Yeah.
So you're saying when one thing moves, everything moves.
Exactly.
Motion.
This is I put that in the book, by the way, to explain what motion is. And I invoke Mr. God, the man upstairs, and he comes in, and God's watching his creation. And aside from God, we're gonna put him aside. He's spirit, so he doesn't move or whatever you want to think of it. He's not an object. So God is a spirit, but he's got this universe in front of him. All the atoms there, and it's a frozen universe. That's what I call it, the frozen universe. What does it take to move the entire universe? All you need is to move one atom. As soon as you move it to the left, everything else moves to the right with respect to that atom. So all you need to get the universe to move is to move one atom. Of course, that never happened. The universe, again, is eternal in both directions of time, if we're going to talk about time, in the sense that there was no beginning to the universe. The universe has always been there. And we have trouble understanding that because we say, well, what do you mean? How can it always have been there? Well, there's no way you're going to answer that question for sure by introducing God or energy. Like, God, for example, Christianity introduces God. The mathematical physicists introduce energy or Big Bang. And then they have trouble explaining, well, what came before? And people say, well, how did the first dot come in there? How did that singularity explode? Where did the singularity come from? Or where did the energy come from if you're going to use the energy explanation? And again, there's no explanation for that. So no matter how you look at it, you're not going to be able to answer it. All you got to make the assumption of is that matter has always been there, and the reason for that is that matter cannot convert into space, and space cannot convert into matter. You cannot have space suddenly, you have emptiness, vacuum, space, void, whatever you want to call it, zero, zip, and suddenly, bloop, you have a 3D ball. No way. You cannot explain what triggered it. Another motion? So we got a problem there. And likewise, you can't have a ball turn into absolute empty space, into nothing. It cannot disintegrate to the point where it converts into nothing. It can maybe transform itself into a square or a cube or some other object, a tree. But it cannot turn into space, into absolutely nothing. It cannot lose length, width, and height. So if matter cannot turn into space, into vacuum, and vacuum cannot turn into matter, we have to assume that the universe or matter has always been there. It's eternal.
If the universe was always in motion, does that mean the universe will always be in motion? By definition?
The universe will always be in motion, yes. In other words,
in
both directions of time. If we're going to talk about time, or in those terms, if we say, well, what is time? Well, time is what we have here on Earth. We humans invented time.
You don't need time. Just the question, the question is, if the universe was always in motion, does that mean it will always be in motion?
Yeah, and again, I say that nothing's going to stop motion. It's impossible to stop motion because it's impossible to stop. It's like, I think it's the same question as saying that, can a ball turn into space? It can't.
Why?
And
why is it the same question?
Well, that's what I'm going to say now. A ball can't turn into space, and in the same way, if everything's in motion, what would stop it? What would freeze the universe? And that's unimaginable. Something external would have to freeze it or put it to a stop, grind it to a stop.
It just slowly winds down.
Slowly winds down. Why would it wind down? Wind down.
It's like when you roll a ball, eventually it just stops moving.
Yeah, but a ball encounters friction, air, gravity. Here we're talking about, this mass of all these objects in it, all these atoms and whatever, and they're kind of spinning around each other and moving around. None of them they can change their position, their location with respect to each other. One planet with respect to another, one atom with respect to another gas molecule with respect to a gas molecule. But what they can't do is scratch their elbows against space. So it's not like the whole mass, which is what we're talking about, whether the universe, the entire matter of the universe can grind to a stop. Why? Because in order for it to grind to a stop, it would have to have friction against space.
Can it have friction against itself?
That's what I'm saying.
Wouldn't that stop it?
No, because what would you have? This has been debated. Like, if all this mass, and again, we're talking about all the objects, were eventually pulled by gravity, right? By gravity. It comes to a ball. Let's assume that's the case, right? So we have all the matter in the universe gradually over the trillions of years, finally comes and forms a ball, right? And the question is that ball static? Or is it spinning? Is it a perfect ball? Is it an irregular ball? And you got to look at these things because maybe the ball is spinning and you still have motion.
You can't have a ball spinning if it's the only ball in the universe.
Well,
Spinning
no. You will have, because the atom that's on this side of this ball
Yeah.
is different than the atom on this side of this ball. So now this guy is moving with respect to that guy, not with respect to the. There's no absolute space out there. We're talking about motion of this guy with respect to this guy.
But it's always the same.
Well, we don't know if it's the same.
Because you'd have to compare it to a third thing that's outside of the ball.
Well, again, the question is whether you're going to get an irregular ball.
Does that matter?
And there's two things. One is if it's an irregular ball and whether things are still in motion. I mean, are we talking about a solid ball that's completely compressed where all, in the case of the threads, right, we're talking about atoms built out of threads and ropes and so on. Are we saying we got rid of all the ropes? We're squashing these things? Again, if you look at how atoms are made with elements are made within the sun, they're being squashed together. Can you imagine all the matter in the universe, all the atoms being squashed? I mean, I don't know what would be inside there. The pressure of that whole thing would continue squeezing and squeezing. Somewhere it's got to go. So I don't think you can imagine this thing in the sense that. I don't think you could imagine it in the sense that it's static, that you just have a ball and it's there, and even if it rolls, it's a perfect ball, and then even if it rotates, everything maintains the same distance with respect to each other. I don't think you can produce that ball with all the matter in the universe. If the universe came together, I think you would have some other physical effects.
Well, my reasoning for why the universe will always be in motion is simply because it always was in motion.
Yeah.
I mean, that is the reason in and of itself. You don't need to try to imagine a static universe. Just the mere fact that it's always been in motion showed that there wasn't a time it started. So if it always was in motion, then obviously nothing can stop it.
Yeah. And this is the issue. Under the rope model, I think that no matter when you are born, whether you are born in this day and age, or if we move 1 trillion years later, I think you'll find the same thing. You'll find galaxies rotating around galaxies and humans being born in some planet and somewhere in the universe. I think that's what you'll find. I don't think that changes ever. So even when we're gone, don't worry about it. Somebody else will come along and they'll have the same discussion we had today. They'll say, what is motion? How did motion start? And all that stuff. And some will go with God, and some will go, the rationalists will go and say, well, let's see, what is motion? That's two locations of an object.
Yeah, that part confused me.
Okay, why?
Two locations of an object could mean the same object with two locations. Like if you have a ball, like a really big ball, you could say that it's taking up many positions.
Well,
if you have a ball,
yeah,
it has many atoms, so you could say it's taking up many positions.
Yeah, but you got to look at what unit you're considering. Are you going to talk about the atom, or are you going to talk about the ball? That you got to identify the system. If we're going to talk about the motion of this ball, right, then we're talking about two locations of the ball. Now, if we're going to talk about an atom, well, let's forget about the object ball. Let's look at the object called atom. Does that atom move with respect to the rest? Does its distance change? So you got to identify the object. That's important. But no, I personally, I cannot imagine how the whole universe comes to a stop. I can't imagine also how the entire universe comes and forms a ball.
I can imagine it.
Well, I don't know, because you got to consider.
Just imagine a really big ball.
Yeah, but see, imagine in that sense, yeah, but I mean, unimaginable in the sense that if you factor gravity and other things and other physical notions that we already have out there,
Makes it easier.
No, it doesn't.
We have a lot of gravity.
Then you can't get it into. Yeah, but see, it's more than that. It's the you got this matter coming together, right? Gravitationally. But once the matter gets crushed, what happens after certain density or a certain mass that you've got together? If we know that some of these stars, which are monsters, and many times the size of our sun, right, and they're big stars, and supposedly they crunch matter and maybe they produce uranium cores for all we know, because they're just so massive that they form all these radioactive materials, the high-level materials, the heavy ones, from the periodic table. And that's a big star. Now, what happens if you take all the matter in the universe and begin to crunch it into a ball? Well, I don't know what's happening. I wouldn't like to be in the center. I'd be squeezed the hell out of existence, And
besides the universe,
yeah.
Besides the universe, is perpetual motion possible? Perpetual motion.
No, in fact, in my book, I say that the only conceivable perpetual machine is the universe. It's the only conceivable machine. In other words, our universe is a closed system in the sense that matter cannot leave space because space has no borders to cross. Space is not a thing. So you cannot escape space. Even God can't escape that which has no borders. So you have all this matter, okay, floating in space, right? And it's all moving with respect to each other. And so the question is whether we can put it to a stop, and I'm saying we can't. So we have perpetual motion. We do have a closed system because none of that matter can leave the space. So we have the two conditions. We have a closed system, right? Everything's contained within space. If we're going to talk about within, there's no within, but all this matter is floating out there in space, as we say. And can it come to a stop? No. And if it can't, then it's in perpetual motion. We have to conclude that not only can matter not convert into space, but it's trapped, it's imprisoned forever, but it's also in motion forever. It's incessant. It moves incessantly.
What are Newton's 3 laws of motion, and why are they so important?
Well, I don't even know about laws, and I don't even know if they were Newton's, because I've seen different versions that preceded him. So Newton kind of borrowed from others. But the first law says, that an object continues in a straight line motion unless it's deviated, unless something stops it. The second one says force equal mass times acceleration, which is his most famous law. And the third one is the clash resistance. That let's see if I can phrase it properly. That one that you move against something. What was it? I'm trying to think about it.
You get a D in physics.
Yeah, I get a D. Today I failed the course, but it's one pushing against another. What was it? One is straight line motion. The other one is force equals mass times acceleration. The third one is something about resistance.
A force is a push or pull that acts upon an object as a result.
Okay, that's what it was. Yeah, but the point is that these 3 laws of motion.
Yeah.
The only one that for one he should get credit is force equals mass times acceleration, because that was new. The first one, straight line motion, several people said that in the past, so it's not a Newtonian law. If we're going to call it a law, it was legislated way before Newton. As far as I know, Descartes also already talked about straight line motion. And the third one, I think also, push and pull, resistance, I'm not sure, but I'm almost sure that people figured that out way before Newton. The only one we should give him credit is for the second one. But should we give him credit for any of them if he never defined the word motion? I mean, how can you give this guy a Nobel Prize for saying, I got the 3 laws of motion, when he hasn't defined the word motion? He says, well, you know what I'm talking about.
Under the rope hypothesis, can it be said that magnetism is in motion?
Magnetism is a concept. What is in motion are the threads.
Can you say that they're in motion? Because they don't have location.
Gotcha. Got me there.
Yeah, we have a problem with some of these concepts when applied to the rope model, and that's it's because we have a problem with using these words in the context of the thread or the rope hypothesis, and that is that, does the rope exist? Well, if we talk about the word exist in the concept of in the context of an object that has location, well, the rope qualifies as an object. It has shape, right? But does it have location? And we covered this in a couple lectures ago, where we said, can you establish a distance between one rope and another? Well, conceptually, I guess you can, but we've never done that in the measuring world. In the measuring world, we measure from atom to atom. Excuse me, and we never measured from rope to rope because we never knew there were ropes there. It's like, and let me put it in a different context so that you see what I'm talking about. If there's nothing between two atoms, if we're just going to talk about distance between two atoms, right? We have distance here and we have another pair of atoms here, we have distance here. Can you take the distance between the distances? That's what we're asking in terms of the rope. In terms of the rope, it makes more sense because now we have an object. We have two ropes, right, parallel one to the other. And conceptually, we can say, is there a distance between the two ropes? And yes, you could define the word distance now in that sense. But then you have the problem is, well, what point on the rope are you going to take? Which little link are you going to take?
Like what if they're like that?
Yeah, I mean, they could be in different positions. They're also moving. Atoms we can deal with because we can't say we see them, but we see the objects they comprise. Ropes, there's no way we're ever going to see a rope.
But isn't it a conceptual issue? I mean, we're essentially talking about measuring, but that's besides the point.
Right. No, all I'm saying is the word distance has traditionally been brought down from mathematics. And so we always have this concept of distance. Yeah, let me get the measuring tape.
Well, back to the question.
We get that, and now the question is, we get rid of the tape. We're not going to do math. We're just going to say, is there a separation between ropes? And obviously there is. But then you get the other issue, and that's if you have a rope, and you're going to talk about the separation, the distance to all other ropes and matter in the universe, it gets very, very complicated because what part of the rope are you going to take in the other side of the universe? Are you going to take the middle of the rope, the ending of the rope? It gets complicated. It's not like an atom, which is like a point particle or a rounded thing that's there. Now you're talking about a rope that extends.
You're talking about a section.
Yeah, and then what section of the rope are you going to take?
Well, just any section.
No, but this is what I'm saying. What I'm saying is that, yeah, there is a distance and separation between any portion of any rope to any portion of any other rope. There is a separation, but it gets complex. And then you got the question of location. What is the location of that rope? And the question is, again, are you going to take a little segment, a little link, or a quarter of a link? How much of the link are you going to take? It's not, again, like an atom, which, atom is always considered. We've always considered as a discrete entity. Now we have an elongated entity. Now to talk about location is very, very difficult.
Well, back to the question, can it be said that magnetism is motion or is in motion?
Well, again, if we're going to strictly by definitions, it's going to be very tough because we have trouble defining what location is, what distance or location is, whether the rope, the rope or the thread exists. Assuming we could get through those hurdles, and I need smarter people who can tackle the problem of definitions there. Maybe there is a way of doing it, or maybe creating some new words specifically for the rope. But once we get past that hurdle, then we can talk about the motion of the thread. Because I am saying that, the thread is twirling, it's spinning.
About magnetism now.
Yeah, magnetism. So we're spinning the thread around, okay? We're spinning the thread around, and it's the wall of threads that come out of all these atoms that are aligned that is swinging around, and that's what the magnetic field is. And yes, if one of the things you'll notice if you go to the YouTube or even just look it up, you'll find that all magnetic fields are always illustrated statically. What moves, they say is, when you, well, not even the iron filing, Pete. The iron filings also fall and they stay in place, right? But what they're saying is moving are the lines of force. The lines of force are the ones that move, not the field. The field is static. It's just a magnet just has a static field. Nothing's moving. But what moves within the magnetic field are the lines of force. And then they say, oh, by the way, the lines of force are inexistent. They don't exist. We just use them to explain, magnetic force. So they use the lines of force to explain magnetic force. They comprise the field, but the field is static. So what we're saying is, no, look, we have threads. Now we're talking about physical object, not about lines, which is a concept, not about field, which is a concept. We're talking about threads, and those threads are what we traditionally called lines of force. The threads are swinging around. They are moving. But then the question comes up, and that forms the magnetic field. But then the question comes up, like my son here asks, very intelligently, he says, well, does it make sense to say that the threads move? And before you can talk about the motion of the threads, you got to go back to location. Before you can talk about location, you got to go back to distance. And now it gets tricky because, again, you know what I said. If you have these ropes, where are you going to measure? Not measure, but how are you going to talk about distance to other ropes? Maybe to atoms, yes. But can you talk about distance between ropes, the separation between all ropes in the universe? Well, again, what chunk of rope are you going to talk about? And all you can do in that case is, maybe this is the solution, and I'm improvising here now. I'm saying maybe you take the full rope. It doesn't matter, because as long as there is a separation, you're not concerned about, well, is it this link or is it that other link?
You mean the full rope between two atoms, not the full,
not
the whole thing.
Right, and we're talking about all the ropes in the universe. If there's gazillions of ropes, then now we have distance separation from rope to rope. There is a separation, a physical separation. We can call it physical here. In other words, there is a separation, a distance. Now, can we measure it? No. Can we stretch our measuring tape across? Well, what link are you going to use? So we're not going to get into that part. But physically, there is a separation, like there is a separation from one atom to all the other atoms in the universe.
Conceptually, too.
Yeah, it's a conceptual issue. And you can say, well, the location of this stretch of rope between these two atoms is the separation, or the distance to all the ropes and matter in the universe. And that's simply the space that separates that rope from all the other matter in the universe. That's all you can do. And then, yeah, you can say that's the location of that rope. And now if you have location, if the atoms move and the rope also moves with them, or in some way moves, because these ropes do move, from one second to another, they're not static in that sense. And so then you can talk about motion of the rope and also motion of the thread. So only in that kind, and also about the existence. You can talk about the existence of the rope.
We're going a little into overtime, but I think this is a good question. Does motion...
Well, hold it. We got Thomas here, has a question.
Wouldn't distance always be the shortest separation between two objects?
Well, it doesn't have to be the shortest. Shortest is a mathematical word, in the sense that you're going to measure and say, well, this one's 10 centimeters, the other one's 20, so the shortest one is 10 centimeters. I don't think you need to introduce the word shortest or longest. I think all we need to do is say, from a conceptual point of view, there is space between this rope and all the ropes and atoms in the universe. There's separation. And that's the location of that rope. Imagine you're God, right? And you say, well, what's the location of this rope between these two atoms, right? Between these two hydrogen atoms, right over here in the middle of the universe. Well, what would he do? Well, he doesn't get his measuring tape. He just looks and says, conceptually, that stretch of rope, that 1 meter piece of rope, right, has distance with respect to all the rest of the ropes and atoms in the universe, all the existing matter. So there is a separation, and we can call that distance to any part of that you choose, and we call the whole shebang location.
Well, I think conceptually we always think of the shortest distance. When I think of two dots, I don't think of the distance between them as this curve,
Yeah.
No one really thinks of it like that.
When we think of distance, yeah, but listen, this is a good question, because when we think of distance, we think of linear space, okay, linear space.
Whatever that means.
Yeah, it's like, no, you got to think of it, if there's something like a line, a one-dimensional line, as they say, just that it has width only or height. If we take that little line, so as thin as you can make it, and you take it from the center of one atom or the surface of one atom to the surface of another atom, well, we call that distance, right? We'll call that the distance. That's the rod that we're going to use to talk about distance. But again, the question is, is that what we're trying to do here? And I'm saying that we should not think of this as just a little line. You can think of it as a plane, If you take two ropes, you can put a plane between them. That's one. And if there's another one on top and the other one on the bottom, the other one on the side, well, now we're talking about 3D. And now we won't use the plane, we'll use the cube. In other words, what I'm saying is that distance in that context, in the context of the rope and in the context of the thread, has to be viewed in terms of, just the space. And you can't talk about linear or think in terms of linear space, but we'll call this 3D space, solid space. We're talking about, a 3D extension in every direction, and that's the location of that rope. If you're going to just talk about that rope, well, that's the location of that rope vis-a-vis the rest of the matter in the universe.
Last question.
No problem. Just keep. If we need to go a few more minutes, we'll do it because the subject is very interesting.
Does motion? You talked about motion being two or more locations of an object.
Yeah.
So does that mean that motion requires memory?
No. In fact, I distinguish memory. I distinguish motion from time, and the difference is memory. Time requires memory, motion does not. And you say, well, how can that be?
Yeah.
I mean, the moon moved, right? But the only reason you know this, or that you're aware of this, or that you observe this, is because you remember the moon's previous location.
That's how you have two or more locations. You can only have,
right?
Everything only has one location, but when
right.
you're talking about two or more.
Okay, now God swings his magic wand and kills all human beings in the universe. There are no more intelligent beings, nothing that is alive. We don't have time anymore because we don't have memory. There's no memory now. Now it's just rocks swirling in space. Do we have motion? Yes, we do have motion because motion is two or more locations. And as long as an object occupies two or more locations, in the absence of an observer, it's moving. So it moves by definition. Time, on the other hand, requires memory.
But an object can only have one location.
Yes. An object only has
So
one location.
Also, according to your definition, nothing's in motion. Since everything only
No,
has
because
one
you don't need
location.
the observer.
No, without an observer, it always has one
Well,
location.
did the moon occupy two or more locations on its own?
It always...
On its own.
It always occupied one.
No.
At one because there's only the present.
Yeah, the present.
There's only the present.
The present, but if you talk about two or more locations, obviously you're talking about a previous...
humans.
No, you're talking about a previous location that the object had, irrespective of the observer. I mean, the moon...
But you're invoking time or memory.
No, you're not.
Talking about two positions.
No, you're
because
not.
Everything only has one.
No,
in
you're
reality.
not. No, because remember, what is location? It's just a set of distances. So if
Yeah.
if the moon occupies two different sets of distances, right, on its own,
Yeah,
we're
on
all
its
dead.
own.
There's no memory. There's no. If the moon occupied two or more locations, that's what we mean by the word motion. We're saying that when the moon, right, takes two or more locations, we'll call that motion. It's a definition.
I think we're going to have to agree to disagree there.
Okay.
Everything only has one position in the present.
In the present.
There's only
in the
the present.
Now that's time.
No, time is when you're
Time
talking
is
about two
the
or more.
No, when you talk about present, you're talking about time. I'm not saying time. I'm saying two or more locations.
But that's time.
Where's time in the definition?
Two or more locations invokes time because everything only has one location.
Yeah, it has.
Unless you invoke time.
Well, if the moon occupies two or more locations, are we agreed that it's got motion?
No, we agree that we're using time. Or memory.
Okay, we'll fight this out. We've got the boxing gloves over there, and we'll take care of this tonight. Now, tomorrow we don't know if any of us two will be alive to be online. We'll see you tomorrow, okay? We'll figure this out. Bye-bye.